almost everywhere some solution need not to be viscosity solution because there might be a bunch of almost everywhere solution, and viscosity solution is the fourth one. Well, not yet. So yesterday I keep claiming that this is the correct one. I need to give you more evidence because you say, okay, that's a selection procedure. What if I do it in a different way? What if I select it in a different way? Can I select another way of solution? Actually, indeed, there's another school of thoughts that consider some kind of symplectic solution, like led by I forgot the name. Led by the guy who was doing symplectic geometry in France, Viterbo. Yeah, Viterbo has another school of thoughts that has a different way to define solution, not viscosity solution, and they don't agree with each other. So there are still different schools of thoughts, but I'm going to try to convince you that this is correct. Okay, so let me give you a proof. So by Rademacher theorem, so this is pretty standard. Maybe it's, if you haven't seen, there's a nice book. This is maybe an okay. Let's say by Rademacher theorem, U is differentiable almost everywhere. So I'm going to prove that at those points where U is differentiable is correct. So type x0 in Rn such that U is differentiable at x0. So I'm going to prove that it's actually the solution at this point. In the correct sense, it is differentiable. Here it makes sense to plug in here. Okay. But remember, the definition of viscosity solution is kind of weird. We need to touch it from above and so on and so forth, right? Okay, so for example, function U can be crazy like this. U, okay, and take x0 to be the point that is differentiable, but it might be not nice somewhere else around. So what I need to do is the following. What I need to do is to, I know that it's differentiable here, there's a tangent vector here, there's a slope here. What I need to do is to design a kind of clever test function space so that phi can still touch this one from above and has the same derivative. Because it's differentiable here. If you touch it from above, it's going to, the tangent line is unique, there's no way out, right? It's differentiable. It's not so hard, but this is also in the paper of MS a long time ago. It's boring. Okay. So designing free. Designing free. Well, you can just sort of think of what you want. I want it to be greater, so now, I know that U is sort of nice in this neighborhood by just normal understanding of differentiation, right? By the way, before doing that, I'm going to assume that x0 is equal to 0. Sorry, I'm going to assume u0 is equal to 0 and du0 is equal to 0. Just say everything is 0. Yeah, you can always subtract those. Leading function. Affine function. Okay, so because I know du0 0 and u is nice inside, so I think I do have ux is basically equals to, it has to vanish of more than one order, so it should be x times the modulus continue to x, something like this. So x has to be like that, right? Where w is the modulus of continuity. Modulus of continuity. The lim of x go to 0, w omega x is 0. Okay, so I have, you must have this form. Okay, after that I'm going to build phi based on this. hope that I remember this one correctly, but it's sort of just like that. So for any r greater than 0, let say rho r to be the sum or the max of x greater than or equal to r, absolute value of w x or omega x. Just take the kind of maximum of the modulus continuity to be rho r. Okay. So of course rho is increasing, right? Sort of making it bigger and bigger and bigger. Okay. So rho 0 is equal to 0 and r max to rho r is increasing. So now I'm going to define phi based on that. So set phi x to be integral from absolute value of x to absolute value of x, rho s ds. And now, I want to make it bend up. I'm going to add any parabola, anything you like. Let's say x to the x squared. You can take x to 2014 and anything you like. This is kind of the thing, when you know that the local maxima or local minima, you can add any parabola, anything like that to make it strict maxima minimum. That's kind of thing. Okay, why do I define this way? You see, rho is increasing, and I'm taking the integral from x to 2x, so it's kind of like a black x, right? A black x. So surely this is going to be greater than u. So what is phi 0? Phi 0 is 0. Which is equal to u0. Okay. For x not equal to 0, what do I have? Phi of x? Well, my crude estimate, this is increasing. It's greater than equals to x times rho of x. Because the length of the interval integration is x, right? That and plus x squared. So this one alone already greater than x times the modulus of continuity. Right? So this is strictly greater than 0 x. Well, x is not 0.
How many dimensions are we talking about?
M. Rn. We are in Rn for n. Okay. So, yeah. Okay. What is d phi? I mean, now we have to differentiate, so that comes to your question. So, of course, we see that phi 0 is 0, and phi is sort of increasing, right? I mean, phi sort of coming up. And now we have to compute d phi. D phi of x. Now you see the reason why we cannot start from 0. If we start from 0, we're going to have a singularity. That's why we have this be a little bit of x to dx, right? So that's really your question. So d phi of x is really equals to what? If we differentiate here, I hope that I don't mess this up, but I think it's going to be rho of 2x times 2x over x minus rho of x over x plus 2x for x not equal to 0. Of course, this one is nice, everything is continuous when x is not 0. Let's see if when x goes to 0, does that go to 0? I think yes. Of course, right? So absolute value of d phi x less than equal to rho of 2x, worst case scenario, plus rho of x plus 2x, going to converge to 0 and x goes to 0. So phi is C1. D phi of 0 is 0. So that's the correct test question you want to design. Right? It's touching you from below, or from above. It has the same radius, d phi equal to du equal to 0. here. Right? And that's why we have to be, this is kind of clever, we have to be careful. If we put from 0 to x0, we're going to end up with a singularity, and I think that comes to the question. That's why we need to move it up a little bit. Does that make sense? Okay, so this is a clever device, and then we have that, and then we touch u from above by this free function. So if we plug in, you're going to have u0 plus, which is 0, h of x, h of 0, the phi of 0 equals to less than equal to 0. And similarly for the touching from below. So that means we really have is a solution at the point x0. Yes?
How do we redo at 0?
How do I reduce to 0?
How do the meter of phi at 0 exist in that way?
Oh, because phi is always greater than equal to 0. So phi of x is always greater than phi of 0. So phi 0 is the minimum of phi. And
so you can differentiate phi when x is not 0, right?
yeah. I differentiate when it's not 0 and
so that does imply that the phi is differentiable at 0.
well, you know, I claim that I can extend it from here to it to be 0 and 0. So just if you want to compute it by hand, okay, that's cool. Yeah, I define d of 0 to be 0.
So you can give the mean value theorem.
Yeah, I'll use the mean value theorem. Because by using the mean value theorem,
You subtract phi x to phi 0 and divide by
yeah, right. This is